Okay, let's get started. So I'm going to start now with a historical introduction to parity violating electron scattering, neutral current interactions in the weak mixing angle, and then this will just connect to what we talked about already yesterday. And then the SLAC E158 was the first of these new generation of experiments. Then QWeak and PVDIS are experiments here at Jefferson Lab. And then I'll talk about the future. All right, so let's get started. So this first slide is to bring you kind of into Jefferson Lab mode of thinking, fixed target electron scattering, right? This is a very famous plot made in what, 1976, okay? Most of you who do Jefferson Lab physics will know immediately that this is elastic scattering of a heavy nucleus. This is lead 208. So clearly these wiggles here tell you a lot about the structure of the nucleus. So this is the so-called form factor, right? This is the Mott cross-section. This is the differential cross-section over 11 orders of magnitude. So this was already, electron scattering was a big deal already in the 60s and 70s. So you all know this, that for a heavy nucleus, this is just a Fourier transform of the charge distribution. And in fact, we now know this so precisely that we know that the nucleus is a diffuse sphere, and we actually know the way the sphere drops off, et cetera, et cetera. So even by the early 60s, we were drawing cartoons like this, primarily due to electron scattering, right? So you all know this is a proton, this is a nucleus. You've seen this in textbooks. It all comes from electron scattering. Now, the other thing also, which is going to be important for us today, is deep inelastic scattering. And if you want to describe, everyone, you've learned about scaling, you're learning QCD, et cetera. But if you want to tell a high school student why we think there are point-like objects inside the proton, it really goes back to form factors. The fact that this is flat is supposed to be the scaling, which you all understand, I think. But the fact that it is flat is the fact that there is no form factor, or the form factor is a delta function. It really is that. Okay, so the fact that you have high rate at high Q squared is going to be important for the parity violation program. But this is something for you to remember. This plot is the Nobel Prize winning plot for Friedman Kendall Taylor for the discovery of quarks in the mid-60s. Okay, so this is just a reminder. I've shown this many times. Then you have parity violation. So now put yourself into a situation where you know about electron scattering, but you don't yet know about quarks. And you now just discovered parity violation. And that was the situation for 1958. Okay, and this was the paper that is the very first mention of parity violating electron scattering. And it's such an amazing paper. It's like 2 pages that I'm going to go over it very slowly. It's got some brilliant concepts that anyone can understand, especially if you have the knowledge that I gave you yesterday. So this is Zeldovich. He's an amazing figure in physics, mostly in astrophysics and cosmology, but he came up with this brilliant paper. Parity non-conservation, the first order of the weak interaction constant, and electron scattering and other effects. Amusingly, you notice that in the former Soviet Union, December 25th is not a holiday. He submitted it on that day. Okay, so what did he say? The brilliance is already there in the first 2 lines. He says, we assume that besides the weak interaction that causes beta decay, now this should be familiar to you. I put a matrix element like this to you when I discovered when I talked to you about muon decay. He says, if that exists, why not this? This is the neutral analog of the charge current interaction. So here it is in cartoon form. He says, if this exists, change the neutron to a proton, the neutrino to an electron, then that gives you this. But here's the brilliant insight. The brilliant insight is that if you have this amplitude, it will interfere with the electromagnetic amplitude. That's the key. because the initial and final states are the same as just electromagnetic electron-proton scattering. That's the key insight, that it will interfere. And there's an interference term. Now, he got excited about something that turned out to be not relevant. He thought he can measure the sign of G because it's always G squared that shows up in the lifetime, right? In the radioactivity lifetime. And he realized that this would be a 1 order of G, but that turns out to be kind of irrelevant. But the fact that it's an interference term is his brilliant insight. And the fact that this is parity violating. And then he constructed the parity violating asymmetry in this language here. In the scattering of fast, in 1958, 1 GeV is fast, right? 10 to the 9 EV. Didn't exist. 1 GeV did not exist in those days. But you'll see why he needed at least 1 GeV. Longitudinally polarized electrons through large angles, then it can be expected that the cross-section for right and left-handed electrons will differ by 0.1 to 0.01%. So that's the cross-section difference divided by the sum, right? That's the asymmetry. Fast, because you need big Q squared, and large angle also to make big Q squared, right? And why did he need big Q squared? So first, let's convince ourselves that if I just flip the longitudinal polarization of the electron beam, it is a parity violating interaction. So if I take this in the center of mass frame, I have the electron coming in longitudinally polarized. Reflection, I will change the sign of momentum, but not the sign of angular momentum. So the spin will stay the same. Now I do a trivial rotation, and if you compare this to this, the only difference is I've changed the longitudinal polarization, right? So if I don't get the same answer, parity is violated. So one of the incident beams longitudinally polarized, change the sign of the longitudinal polarization, measure the fractional difference. So why did he need a big Q squared? He was taking pity on the experimentalists. He wanted a big effect, right? Consequently, the ratio of interference term to the Coulomb term is K squared or E squared. In modern language, we write it like this. The electromagnetic amplitude is 4 pi alpha over Q squared. The weak amplitude is G Fermi. And so it's G Fermi Q squared over 4 pi alpha. That's about 10 to the minus 4 Q squared and GeV squared. And that's how we got the 0.01%. If you take G Fermi, this is roughly what you'll get. Okay, so he was able to show that, in fact, this would be a way to show that there's a neutral current parity violating interaction. Okay, now this was 1958. People didn't know how to do such an experiment then, and people didn't even know it was worth doing, right? But then in the 60s, we got this, right, which we already went through. We had the SU2 cross UY proposed with the Z0 as the neutral current. So now perhaps it becomes relevant, but it became extremely relevant for the following reason. In the early 70s, the first neutral current event was seen in a bubble chamber in neutrino scattering. Okay, so this was CERN bubble chamber discovery. And this was the first time they could measure the cross-section for anti-muon neutrino nucleus scattering, and they measured sine squared theta W for the first time by measuring this cross-section. So this was the full, from the Weinberg model, the full Feynman coupling, Feynman rule for the FFZ0 coupling, right? So you have the vector piece and the axial vector piece, okay, for each fermion. That's what the Weinberg model predicts. So it's something you will not see in textbooks, but historically, it's very interesting to see how things evolved historically. In the mid-70s, Weinberg model was there. It's who Weltman paper had come out. People liked the electroweak theory, but there were alternatives. So remember how in the electroweak theory, you have the left-handed fermions in an isodoublet and the right-handed fermion in a singlet, right? But there were alternative theories where there was a heavy neutrino and the right-handed electron was in a doublet. And it turns out that the way these couplings evolved, when you have a doublet here, would get rid of the parity violation in neutral currents. So this was a big deal in the mid-70s. If you don't see parity violation in electron-proton scattering, then the Weinberg model is wrong. Okay? So that's the situation. And it got worse because there were atomic parity violation experiments done where you can actually, in a tabletop, try to look for the neutral current. This has been developed over the past few decades. And they didn't see the effect. They said they don't see it. So it became a very important thing. And by then, scaling had been discovered, and you could get large rate at large Q squared. So this Zeldovich prediction could perhaps be tested in experiment using deep inelastic scattering, okay, which didn't exist when Zeldovich wrote the paper. Deep inelastic scattering was not known then. But given that in the 60s, scaling had been discovered, you could now think about doing deep inelastic scattering and look for parity violation. So this became a big deal. And that led to the SLAC E122 experiment that launched this field of parity violating electron scattering. So this was 1978 was the publication. So I show you the basic idea of all these experiments. They haven't changed over 50 years. This nice diagram from 1970s technology kind of describes how such experiments are done here at Jefferson Lab even, except we don't have a microcomputer anymore. Hopefully we have picocomputers. So here is a polarized electron source. We have one here at Jefferson Lab where you bring a laser beam to a gallium arsenide photocathode. That is exactly what you have. I don't know if you had a tour. This was invented for this experiment. Okay, such a polarized source did not exist before this experiment. So you bring a laser beam, you have a device called a Pockle cell that takes linearly polarized light and converts it to circularly polarized light. And the big deal is that when circularly polarized light hits a gallium arsenide photocathode, depending on whether you have right or left circularly polarized light, you get right or left-handed polarized electrons coming out. So this is the way you polarize the electron beam. And the big deal about the Pockle cell is that you can do this rapidly without changing the properties of the left and right-handed beam too much. And that's a big deal, okay, to do this kind of experiment. So this high voltage pulse, the polarity of this high voltage pulse will decide whether you have right circularly polarized light or left circularly polarized light. Another very important feature is this half wave plate that you put in the beam, because when a circularly polarized laser light goes through a half wave plate, if it is oriented correctly, then left circularly polarized light can become right circularly polarized light and vice versa. And so by simply inserting this half wave plate or not, you can change the sign of the effect without changing anything else. So that's a big deal as a test of your experimental setup. And then the idea is that you have time slots of right circularly polarized light, left circularly polarized light, then maybe left and then right. You randomly choose whether you start with a right or left. And then you analyze the data as a right-handed pulse, a left-handed pulse, and so on. You have to make sure that the beam is the same for right and circularly polarized light, so you need very precise monitoring. You need a high-power cryo target. Jefferson Lab is the world expert in this these days. You need a polarimeter. The molar polarimeter was invented just before this experiment, and we use it here all the time. Magnetic spectrometer, we use that here in holes A and C. And then for this kind of experiment. And then flux integration. This is another big deal. You're measuring a small asymmetry, you have very high rate, you don't have time to count individual particles, so you use a magnetic spectrometer to send the signal of interest to a region that is otherwise free of background. And you just put a detector there, And typically, you put a pure Cherenkov radiator, and then you just take the Cherenkov light, you integrate the Cherenkov light as a measure of the flux, because you're just measuring a ratio, so you don't care about absolute normalization. Okay, so flux integration was invented also as a technique for this experiment. So here's the data. This is the smoking gun kind of result. This is 10 to the 5. This is units of 10 to the 5. So, 10 here is 10 to the 5. So, this is 10 to the minus 4 would be 10 units here. So you can see the asymmetry, and the points here are the open and the closed, the solid points are essentially the orientation of this half-wave plate. So they're changing it in these as the runs go on, and you see that the sign of the effect is flipping. It's a big deal. So it's a very small rate here. So this is 3 times 10 to the minus 4. It's a small effect, just as Zeldovich predicted. But in fact, they did see the asymmetry, and the lore in the community is, I've heard this from the folks who did this experiment, is that Weinberg and Salam used to call them to find out what the answer is, because they knew their theory depended on the answer of this experiment. They used to get phone calls like, when are you done with your analysis? But they did see parity violation. They measured the weak mixing angle. And it is not a coincidence that this was published in 1978 and this Nobel Prize was awarded in 1979, because of the controversy I told you about that existed in 1975, right? And to accentuate the point, this is the Nobel press release from October 15, 1979. Of special interest is a result published in the summer of 1978 of an experiment at the Electron Accelerator at SLAC in Stanford, USA. In this experiment, the scattering of high-energy electrons on deuterium nuclei was studied, and an effect due to a direct interplay between the electromagnetic and weak parts of the unified interaction could be observed. This is directly from the Nobel press release. Right? So this was a seminal experiment, and it launched the whole field. Now, at the same time that this experiment was going on, ideas were for scattering of nuclei, which is what we do here at Jefferson Lab, was also proposed, but it turned out that for various technical reasons, it took much longer than the SLAC experiment. So it's these experiments here, carbon-12 at MIT Bates, and the beryllium quasi-elastic scattering experiment at Mainz were both started in the 70s, but it took till the late 80s before they were finished. But they did, in fact, publish these much smaller asymmetries. And the idea, the motivation for this is to test the neutral current coupling for each quark. So if you now take a model independent point of view, you have left and right-handed vector and axial vector couplings, and you have up and down quarks, so you have 4 couplings, depending on whether your electron is vector or axial vector, and whether you're dealing with up quarks or down quarks. So we call them C1U, C1D, C2U, C2D. These are the 4 couplings. The standard model makes predictions for all of them, but the idea is by scattering of different nuclei, you get different linear combinations of these couplings. And so it was motivated to measure these. So these were the first measurements of electron nuclear neutral current weak interactions. The pushed experimental technology spawned a new generation of experimenters and experiment, including myself. And then 100 parts per billion systematics, hundreds of megahertz of rates. These were things that were done here. So this is the kind of plot we like to show. This is kind of all the parity violating experiments in one plot. The y-axis is the error in the experiment. The x-axis is the actual value of the asymmetry that was measured. Here is SLAC E122, 10 to the minus 4 asymmetry, few parts of 10 to the 4 error. And then all of these experiments here are kind of chasing various other physics topics, whether it is strange quark studies, neutron radius. I will discuss these in the second lecture. And then standard model tests, which is the rest of my talk here. The state of the art now, which we need for molar, which I will discuss later in the next half hour, is subpart per billion statistical reach systematic control. And normalization is also a big challenge. You're going this way, 100% measurement, 10% measurement, 1% measurement. And you notice that we are approaching the 1%. There is even an ambitious goal to try and measure to better than 1% in the future. Okay, so now I'll talk about SLAC E158, the Jefferson Lab experiments, Q-week and PVDIS, and then talk about future experiments. Okay, so now I won't be talking at all about all these experimental things that we had to struggle with over decades. Photocathodes, polarimetry, high power cryo targets, nanometer beam stability, precision beam diagnostics, low noise electronics, radiation hard detectors. This is all the stuff that we worry about here at Jefferson Lab to do molar, for example. Okay, so one thing I want to emphasize to make connections to yesterday's lectures is that I talked about how we are searching for new physics, and it's really this fourth category that we are in. So we talked about all of these violations of various symmetries. We are talking about violation of parity with flavor conservation. So that's the real niche in these six-dimensional operators I was talking about yesterday. And this is what we are looking for. We are not really in the business of measuring weak mixing angle per se, though that's how we would put it in textbooks. We are trying to see whether we get the wrong answer, so that, because if we did, that would mean there are new physics components, right? Okay, so SLAC E158. So now the 70s, 80s, these experiments were developed. And then in the mid-90s, I talked about the LEP era, how you had the Z resonance, and you had these spectacular measurements of the weak mixing angle coming from the collider, E plus E minus collider. So these are very precise measurements that existed in the mid-90s. And they were looking for new physics in this fashion. There were all these phenomenologists worked on trying to put constraints on new physics that could appear in loops. But just precisely these six-dimensional operators, which we have talked about, do not directly couple to the standard model gauge bosons. They are four Fermi interactions. And in particular, if you're sitting on top of a Z resonance, if you're sitting on top of a resonance, the amplitude is imaginary, and there is no interference term. So for them to see these effects, it will come in with a square. There's no interference. So whereas if you did low energy away from the Z resonance, like we do here at Jefferson Lab or at SLAC with fixed target, then you can, in fact, get an interference term, and you get more sensitive than sitting on top of the resonance. So this is a unique role for low energy neutral current measurements. So that was realized in the early 90s, and that gave the motivation to do the SLAC E158 experiment, parity violating electron-electron or molar scattering. It's a rare opportunity because it's a purely leptonic interaction at low energy, right? It's just 4 electron, 4 Fermi interaction. And it's G Fermi times the quantity we call the weak charge of the electron, which the Weinberg model says should be 1 minus 4 sine squared theta W plus radiative corrections. Okay, so the key is because sine squared theta W is close to 1/4, this number is small, and therefore fractionally, by making just a 10% measurement of this weak charge, you can get a 0.5% measurement on the weak mixing angle. Okay, so this makes the experiment challenging yet easy at the same time. Challenging because the asymmetry prediction is small, but the normalization requirement is less, right? You don't have to measure things to 0.5%, you just have to measure it to 10%, right? Which is good for systematic control. So, of course, we are after not just measuring the weak mixing angle, but looking for new physics. And to emphasize again, you are looking not only for the interference with the weak neutral current, but also with new physics. Okay? Now, molar scattering is special because it is identical particles. And so you have the direct and exchange diagram, which is not true for elastic scattering of the proton or a nucleus. So that brings in some quirks, which we exploit here in molar, which I'll talk about later. The asymmetry is tiny for two reasons. One is 1 minus 4 sine squared theta w small, and the other is because q squared is small, because in fixed target, q squared is 2me times e beam, and me, because you have an electron target, is tiny, right? So this is like 10 to the minus 8 times the beam energy. And so when we realized this, we said, where is the highest beam energy in the world with polarized electrons? And that was SLAC. So we proposed this experiment at SLAC, 45, 48 GeV beam. So this was proposed in 1997. The asymmetry is 200 parts per billion, which is much smaller than what was originally done in the previous experiments. So this had to push technology in various ways. This is end station A at SLAC. So this is an aerial view of SLAC. It's called the 2-mile Linac. This is about 2 miles long. This road here is the Interstate 280 that connects San Francisco and San Jose. The accelerator goes under it. Here is the SLAC complex, and end station A sits here. This is a picture of end station A taken by a professional photographer. He actually took all the technicians, told them to find all their pickup trucks, and ride around with the accelerator and brake both engaged. He had this idea to make a picture like this. You can see the accelerator here, and you can see the interstate right there. Okay, so this is end station A at SLAC, where this experiment was done. So inside the end station, you have polarized electron beam, a liquid hydrogen target. You have these 3 giant dipoles, then followed by 4 giant quadrupoles. SLAC had them because these were the same dipoles and quadrupoles that were used to discover quarks. They were just sitting in storage. They were being very expensive to make them from scratch. Here you can see the massive dipoles. These gentlemen here are installing lights. Why are they installing lights? Because that entire thing was going to be enclosed in concrete because of all the radiation that would be generated when the beam went through here and went veering off through the dipole. Okay, so there were a lot of technical challenges. I won't go through this in terms of high radiation, high electron rate, full azimuthal acceptance, et cetera, et cetera. Number of technical challenges. This is the result. Asymmetry going up and down, we always do that. Apart from the half wave plate going in and out, which is the standard thing to do, SLAC had one other thing that we did. We ran the experiment at 2 different beam energies, 45 GeV and 48 GeV. Why did we choose these 2 energies? What it has to do, if you look here, the beam comes through the 2-mile Linac and then bends 24 degrees to get to the end station. This is that big giant concrete bunker I showed you before. This 24 degrees makes the electrons do G-2 precessions. And 45 GeV is 14 precessions, and 48 GeV is 14.5 precessions. And that allows you to change the sign of the effect. So we had 2 ways to flip the sign of the effect. 45 in, out, 48 in and out. And I average all of these 4 kinds of measurements separately, and I remove the minus sign, and they fall right on top of each other, which is a very powerful way to show that you don't have any additional systematic effects. So I average these 4 measurements. I get this 131 parts per billion with this statistical 10 parts per billion systematic error. This was published in 2005. So what are the implications of this experiment? 3-level prediction was 250 parts per billion, but we measured 131 parts per billion. We did not call a press conference. We just published it because it was actually the right answer. Why? Radiative corrections. Okay, so this is a first demonstration of the running of the weak mixing angle. This is the prediction when sin squared theta w does not run. So just to give you some sense, so these are the diagrams, okay? So again, this is why we had the lectures yesterday. I wanted to show you how the electroweak theory works, how it works at the level of radiative corrections. This was the first cartoon drawn by Bill Marciano, very well-known phenomenologist. He drew, and then this was the situation. You know, this was the precise measurement at LEP, and these were the only two measurements there, and you really couldn't tell that sin squared theta w runs. You know, that's primarily this diagram right here. Okay? Slack E158 ran, this was the current situation, and we were able to show that in fact, this measurement and this measurement are 3% different, 6 standard deviations. We were able to show that sin squared theta w runs, showing that these diagrams were in operation, right? But of course, we are also looking for new physics. So when we published it in 2005, we were able to put new limits on the 4 6-dimensional operator combination, which was unique to E158. The plus sign here is what the collider could measure, and we measured it with the minus sign. Looking for new z primes were as good as the limits that were coming from Fermilab. And then molar scattering is also sensitive to some lepton number violating amplitudes. This is the first search for such lepton number violating amplitudes. Okay, so now I want to pause here to show this is the main reason. These two plots together is the main reason we had yesterday's lectures. Okay, you want to understand the standard model. You want to understand how we do BSM searches and how we present the motivation for experiments like this. Okay, so this is it, right? The running of the weak mixing angle, electroweak radiative corrections, and looking for new physics. Okay, so this was a big deal. We published it in PRL because that's what we do. But there was a Nature article, electrons are not ambidextrous. The best low energy measurement yet obtained of the electroweak mixing angle. Central parameter standard model is the last hurrah of Stanford's powerful two-mile linac. So after this experiment, SLAC was shut down as a linear accelerator, right? It became a synchrotron lab, right? And so this was the crux of the article. Okay, so now we come to the overall bigger picture. So here I show you the running of the weak mixing angle and all the measurements are high energy. By the way, all of these red points are supposed to be at the Z resonance. They've just been split apart in order to be able to see them, okay? So they all belong over here. Okay, so Tevatron, LHC, LEP, SLC. These, on the other hand, all these are actually at the correct value of Q squared. The red ones are publications. Q weak and PVDIS I'm going to talk about. These are the two measurements I'm going to talk about. I'm not going to talk at all about NUTAV, deep inelastic neutrino scattering. So E158, so molar is, this is the error bar we are projecting at this Q squared. Here is E158. Here's Q weak. And then this is solid is another idea. And this is minus P2. So these are the 3 yellow ones. I will discuss them as we go along. Okay, so back to this kind of picture with up quarks, down quarks, and electrons as targets. Back to the same thing I showed you before, the standard model predictions, but you're looking for new physics. And the reason you want to do all of it, you want to do elastic scattering, such as Q weak, and atomic parity violation to get at the C1, which gets to this linear combination of new physics amplitudes. C2 gets the deep inelastic scattering experiment is the only way to get to the C2s. And that gets to these linear combinations. And then molar scattering, of course, is for electron-electron scattering. So all of these are worth doing because they're probing different 6-dimensional operators. Okay, so past JLab experiments, Q weak, the weak charge of the proton. So this was a big endeavor here from roughly the mid-2000s to mid-2010s. This was in Hall C. So elastic scattering at very low Q squared can be written in this form. This is the standard model piece, Q squared times the weak charge of the electron. And then there is a structure piece. You can just put it all together due to the form factors in here like this. And then the weak charge is proportional to 1 minus 4 sine per theta W, or in the language of the C's, 2C1U plus C1D. So this is just elastic scattering. There were 2 production runs in 2011 and 2012, was published in 2018. Here is the asymmetry measurements. They also did a G-2 flip, and they flipped half-wave plates, et cetera. You can see 200 parts per billion, roughly the same size as the effect in SLAC E158. Here is the Q-weak spectrometer in Hall C. And there were these 8 quartz bars. And each of these quartz bars is right here where the elastic scattering went. You can see here, this elastic scattering, this is inelastic scattering here, and there is a gap. And so this experiment was done and got a very precise number, which is shown here. What are all these numbers? You have to wait for the next lecture, because these are the other experiments we were done previously, but it allowed you to get the very clean extrapolation of this to Q squared of 0, which is the standard model test. Okay, so that allowed you to get to the weak charge of the proton. This was the final result. And in this running curve, this was SLAC E158, this was Q weak. And then in terms of the C1U and C1D, you get 2 linear combinations from atomic parity violation and Q weak, and you're able to separate them, and this black is the joint fit of the 2 measurements, and that allows you to test new physics at the multi-TeV scale. Okay, so that is Q weak. And then PVDIS was an experiment in Hall A, parity violating deep inelastic scattering. And the idea here is if you use a deuterium target, just like the SLAC E122 experiment, you are able now to just describe the asymmetry. You always get this G Fermi Q squared over alpha in all these formulas, but then you have an A, now in terms of Bjorken X, you have an A of X plus a kinematic term in terms of Y times B of X. And the key thing is that DIS gets that to the B of X, which gets you this combination C2U minus C2D. So that's the focus, is B of X, because A of X is measured by Q weak and atomic parity violation. So these were the 2 results at Q squared of 1.1 and Q squared of 1.9 that was done in Hall A. And this is sort of the C2U minus C2D, C1U minus C1D combination. This was SLAC E122, and this was the JLab measurement. If I zoom in there, you see here, this is the SLAC measurement, and this is the JLab measurement, and combined with the other measurements, you get this red ellipse, which is non-zero. So this is the first time that you were showing that the first determination that the axial quark coupling combination is non-zero, and then you also got nice limits on new TeV scale physics, and this also led to a Nature article. By separately scattering right and left-hand electrons of quarks in a deuterium target, researchers have improved by another factor of 5 on a classic result of mirror symmetry breaking from 35 years ago. Okay, so that was the PVDIS experiment in Hall A. All right, now we come to the future. So I will now spend a little bit of time on the molar experiment. So molar is a large project that is being, at the moment, constructed. That's why I'm here, actually. I'm on sabbatical this year, watching the construction of molar. The commissioning we expect to do in early 2027. This is what we think it's going to look like in Hall A. This is beginning to take shape. If you go to Hall A, you'll see these things are beginning to be installed. The high resolution spectrometers have been put at 140 degrees and 90 degrees this way to be out of the way. So it's the same kind of deal. You have a liquid hydrogen target, collimator, spectrometer, drift region, detectors. So let me just go through this. So first of all, the reach. The prediction is, I'm losing battery here, so I'll just change over. Yeah, but this should work, right? I turn this on. Yeah. Yeah. Okay. So what is the new physics sensitivity? This is the prediction, 32 parts per billion. We want to get to 1 part per billion, and we'll measure the weak mixing angle to very high precision, 0.1%. So the main thing is the new physics. And it turns out that if you compare this to the best high energy collider, that is LEP 200, these are the sensitivities, and compare that to what molar can reach, which is like 20 to 30 TeV. And so molar is accessing discovery space that is more like a 500 GeV linear collider, right? So that's the motivation for this experiment. A 500 GeV linear collider may exist in the 2040s, we don't know. But we are getting to that level of sensitivity right now. Okay, so molar is got some very demanding things, a 134 gigahertz electron rate. We need sub-nanometer control of the beam, very long liquid hydrogen target, very high power, very complicated spectrometer. We need beam polarimetry to 0.4%. But we have a great team because of all of the experience we've had from the previous round of experiments. Okay, so I'll talk a little bit. Here's the liquid hydrogen target. I can show you pictures because it's going on all around you here. So this is the liquid hydrogen target, the way it's supposed to look. This is actually it being constructed right now. This is the spectrometer. And here I will pause a little bit to talk about why we have an odd number of coils. If you count here, there are 7 holes. So you have 7 acceptance holes. Why do we have 7? So we are taking advantage of the fact that we have identical particles. When Q week was done, they had 8 holes, and they had 50% azimuthal acceptance. We also needed a toroidal spectrometer, and that means we would lose 50% of our acceptance because you need to put the toroids in, right? But we didn't want to lose that. So we came up with this idea that because you have identical particles, you can have, if you collect scattered electrons from both 3 GeV all the way up to 8 GeV, they effectively are backward in the center of mass and forward in the center of mass going through the same hole. If I pick up both the forward and backward center of mass electron scatters, I don't need to measure anything on the other side because it's just a partner. It would be double counting anyway. And this only works for identical particles. Okay, so we were able to double our acceptance by having an odd number of coils. So then we tried 3, 5, 7, 9, 11, and for various engineering technical reasons, 7 was the sweet spot. Okay, so this is a very complicated magnetic spectrometer because you have to pull 8 GeV particles all the way out, and you barely want to tickle the 3 GeV particles so that they end up in the same place. This is the heat map of the scattered flux at the end of the spectrometer. The red is the highest heat. These red stripes here are molar scattering, and these smaller red stripes here are EP scattering. If I take a radial distribution here, it'll look like this. Elastic EP scattering at 0.7 meters and molar scattering at about 0.95 meters. That's what this is. Okay, so you want to pick up both. Spectrometer construction, just pretty pictures. More pictures. It's all going on all around you. That's all I do right now is on sabbatical. I just go around with my camera and take pictures. Okay, so the detectors. This is a cartoon I drew in 2010. It's kind of scary how long ago that was. Here are the EP scatters, molar scatters. I told you how they separate out. And this is kind of the cartoon of what we wanted. We needed gem detectors to do tracking. We wanted to actually do the integrating detectors here. We needed a shower max detector, and then we need pion detectors behind a hunk of lead, et cetera, et cetera. It doesn't look like that at all right now. Kind of was a cartoon. So this is kind of tells you, you have to intercept the primary flux. You need to have a redundant way to measure this asymmetry, so you do it two ways. You need to calibrate the spectrometer. That's why you need the gems. You need to measure the part per mil pion muon background, and so you have pion detectors. So each of these colored boxes point to specific detectors here. Okay, so you have the gems, the thin quartz, the shower max, the pion detectors, and then you have various auxiliary detectors for background and calibration studies. And you run the experiment in two modes. The integrate mode is where you take the asymmetry data, but then you put gems in and do calibration in counting mode. Okay, they're where you detect individual particles. All right, so capturing the scattered flux is shown here. So this is a complicated mechanical structure that we came up with. And then you have both azimuthal and radial segmentation, which is shown here. These are all individual fused silica tiles, pure Cherenkov radiators. You have to very carefully design this to have very little material because scattered electrons go through fused silica and then they go through the air light guides of the other detectors. So you have to be, this is a very carefully designed, thin aluminum frames for everything so that you don't make background as you make these measurements. I will skip through this given the time, just to show you how we plan to put this together. This is actually going to happen in the next month. This operation of putting these on, if you go to Hall A, you will see these kind of segments still sitting around like this. And they're going to be launched and put down in there into this rotating wheel. That's going to happen in the next few weeks. I'm just going to flash this. How we do the asymmetry analysis is going to be very complicated. This is now a detailed Monte Carlo simulation of the elastic EP and the radiative tail, the molar scattering, and then inelastic scattering in green. And then you have scattering from the aluminum windows that is shown here, which we can ignore for now. The key thing is this inelastic scattering, asymmetry is much larger than molar scattering and elastic EP scattering. And so there are going to be tiles where you're going to be able to have this stick out. Even though you have very small rate here, you have a very large asymmetry. So by measuring all these separate asymmetries, all of these tiles, you're measuring the asymmetry separately, you're going to be able to unfold out the elastic EP, the molar scattering, and the inelastic EP contributions. Okay, so that's going to be a nice challenge in the analysis for the grad students and postdocs doing the experiment. Okay, so I'm going to skip this part about why the inelastic EP is interesting. If someone has a question, we can go back to that because I want to take 10 more minutes to finish. Is that okay?
Yep. Yes.
Now I'm going to talk about the other future experiments. PVDIS at 12 GeV. Okay, so this is a solid concept. So the idea is to bring a large solenoid, and then we have very high luminosity at 11 GeV. You're still looking at the same asymmetry that PVDIS measured, but now because you have this very large acceptance, you can make a series of separate asymmetry measurements just by making cuts on E prime. Okay, each one of these dots could be a asymmetry measurement, and you have enough statistics to measure the asymmetry many, many times at 0.5% level. What is shown here is the statistical error at in percent. So this is 0.58%. So you make a whole bunch of these measurements. Now, if you're at low X, there could be C quark contamination, and you need to worry about that. If you are at high X, you could have charge symmetry violation, which will change the standard model. By comparing results at different Q squared, you can look for higher twist effects because you should get the same answer. And so by doing all of these control measurements, you're now able to confidently look in this sweet spot at about x of 0.4 and a q squared of 7 and do the standard model test. That's the idea. Okay, so the strategy is sub 1% precision over broad kinematic range, sensitive standard model test, and detailed study of hadronic structure contribution. So these measurements are going to be interesting to learn about hadronic physics as well. Okay, so this is a solid concept. Now, this is not funded yet by the DOE, but it's a very interesting concept that we hope will happen in the future at Jefferson Lab. This is the showing you how, I won't go through this in detail, how this is the original PVDIS experiment, and this would be the reach from solid in terms of TeV scale. And in particular, solid is sensitive to something that the LHC cannot see. The concept is a leptophobic Z prime. What is a leptophobic Z prime? It is a Z prime that doesn't couple much to electrons at all. Now, the way LHC will discover Z primes, if there is any, is by looking for Drell-Yan. So in the Drell-Yan process, you do need the Z prime to couple to electrons or muons. If they don't couple, you're not going to make them, or you're not going to be able to produce them in lepton pairs, right? And you're not going to see hadron invariant masses above the QCD background. So in solid, though, because of the fact of this diagram at radiative corrections, you can see that even though this coupling is just a photon, this coupling is a Z prime, you got QQ here. And so you get sensitive to this at the level of radiative correction. So that's an example of why you want to do such a measurement. Okay, now P2 at Mesa at Mainz in Germany is going to try and improve on Q-weak at JLab by a factor of 3. So that's also a big challenge, big experiment like molar, 28 part per billion, and they're trying to measure that to 1.8%. and get the weak mixing angle to 0.15%. They also have very long-term plans to do this on a carbon target and try to measure the weak mixing angle with a different linear combination of C1 and C2. Okay, so this physics program is supposed to start in 2027. And I'll tell you why they're also going to do a lead target in the next lecture. So this sort of summarizes the physics reach of all the old experiments and the new experiments, showing you what was done and what is being planned. And this triad here is supposed to show you that it is important for new physics to do purely leptonic, d-quark dominated, and u-quark dominated neutral current searches in order to be comprehensive as much as you can. And here's an example of something called a dark Z as to why you want to measure it at low Q squared. Why do you need to have sine squared theta W at different Q squared values? Because you could have something called the dark Z boson that will deviate, that will make this running curve change. Okay, so you want to try and test for that as well. All right, so I think this is my summary slide. I think that's right. And then we can pause. So parity binding electron scattering was central to the development of the Glashow-Weinberg-Salam model of electroweak interaction. SLAC E158 was the first precise measurement of the weak mixing angle at low energies. Demonstrated the potential of low energy BSM searches in neutral currents. JLab PVS experiments have pushed technology to new levels of sensitivity and have the best limits of new semi-leptonic neutral current interactions. Future program, Molar will begin physics next year, and 2 other experiments to push the semi-leptonic neutral current experiments have been proposed. So that's sort of the overall picture in terms of BSM searches. So now you can take a break. I can answer questions, or we can just take a break now, and then we can do the entire question later, whatever you want. And then we also have what I will do after the break is to talk about how, if you assume the standard model, you can probe aspects of hadron structure. Okay, thank you.